So, but for now, I feel like there's a lot less of you than there normally is. And it's not like it's super early, so that's weird. All right. Well, regardless, let's talk about a couple of different applications of physics. Um, one of which is work. So in a standard like first course in physics, like an algebra-based physics course, you're taught that so algebra-based physics. Um, you're often given the formula W is equal to F times D, or work is a force over a distance. Basically, the amount of work it takes to do a task is the amount of force that it takes to that is applied to an object times the amount of distance that that object is moved, right? So this works fine if the force is constant. For example, if you're like lifting a bucket with a string that has a negligible weight, then the only mass that matters is the bucket. So it doesn't matter that much that the length of the string and therefore the amount of string um, that you're lifting changes. However, in the real world, forces are rarely constant. Um, so uh, it's better. So forces in the real world are rarely constant. So instead, we use an integral model where the we get W is equal to the integral from A to B of f dx, where um, B, A, and B is the interval distance over which the work is done. And f is a function for force. Note that this, for us, f will always be a function of the amount of distance that's remaining, because it doesn't actually, we don't have the tools to deal with like force that's a function of time or something like that. That's a little trickier. So note that if f is a constant, so I actually should make that. Note that if f is constant, this results in exactly the simplified model work is equal to f times b minus a, where b minus a is the width of this interval, a to b. Therefore, it's actually just the distance that the force is applied over, right? So there's a couple particular examples that I want to look at. Firstly, I want to look at springs. So springs are basically the force done by a spring is governed by something called Hooke's law. Which says that the force F to stretch a spring X meters from its natural length is F equals kx, where k is the spring constant. The spring constant varies depending on the spring. Some springs are very stiff, and it takes a lot of force to move them back and forth. Some springs are very loose and do not take very much force at all. Like think about the spring in like a pen, like a clicky pen, versus the springs in the shock absorbers in your car. Right, the springs in the shock absorbers in your car are constantly under the force of several thousand pounds, or well, more than 2,000 pounds probably. And this spring in your clicky pen, you can just click with your thumb. So generally, if so, this is pretty straightforward. If you know what K is, but oftentimes when dealing with spring problems, you'll be asked to solve for K. So let's do an example here. So a spring has a natural length of 20 centimeters and a 40 newtons force is required to stretch the spring to a length of 30 centimeters. How much work is done stretching the spring from 35 centimeters to 38 centimeters? So the first thing I want to do with this problem is I want to note that Hooke's law has to do with meters, and in general, we want to be working with meters in this situation. I think that if you don't bother converting, because the answer you're looking for, um, no, you'll get the wrong answer because it'll be your instead of your work being in Newton meters, it'll be in Newton centimeters. So you do want to convert. So I'm going to convert all of these numbers to meters. So the natural length or equilibrium is 0.2 meters. It takes 40 newtons to stretch to 0.3 meters. Or this means that in this case, if we want to solve for the spring constant, we can take that F is equal to kx, where x is distance from equilibrium. And in this case, we're given a value. We know k is constant. Our value of x will be the distance from the natural length of 0.2 meters to 0.3 meters. So f will be k times 0.1. But f is, 40 will be equal to k times 0.1. So we can multiply both sides by 10 to get our k value of 400. Now we need to set up our work integral. So our work integral will be the integral from a to b of f of x dx, where f is our force function, and a and b are our bounds. Our bounds for this are going to be the given distances. Notice that these are distances stretched from equilibrium. So this 35 centimeters is really 15 centimeters from equilibrium, and this 38 centimeters is 18 centimeters from equilibrium. Converting those bounds to meters, we get 0.15 to 0.18. And our force function is kx, so that'll be the integral from 0.15 to 0.18 of 400x dx. We can take our antiderivative, giving us 400x squared over 2, evaluated between 0.15 and 0.18, or 200x squared, evaluated between 0.15 and 0.18. And when we do that, we end up with our answer of 1.98. And the unit for force is joules. Same as energy. Or the unit for force. Sorry, I said the unit for force. The unit for work is joules. Does anybody have any questions about this spring problem here? So the idea essentially is we're given a spring, we're given its equilibrium length, and then we're given some example of stretching it, right? We're going to use that example of how much force it takes to stretch it to blank distance to solve for what the spring constant is, what k is. And then we just set up k in the integral to solve the actual answer, asked question. No. Where am I dividing the length by half? So equilibrium is at 20 centimeters, right? So first off, 18 is not half of 38. So what is the equilibrium position for the spring? Yeah. So what is the distance between equilibrium and 38 centimeters? Yeah. So it's these come from these are the distances from equilibrium. All of your distances need to be reframed as the distance from equilibrium. Basically, what you're doing is you're reframing the problem so that your zero is at the point of equilibrium, because that's where your force will be zero as well. If we didn't do that, we would need to deal with a substitution the entire time, and I don't want to deal with that substitution. So, any other questions? All right. Let's take a look at another type of example that I alluded to a little earlier. So generally, when lifting objects, oftentimes in a first course in physics, you're sort of taught that you can ignore, like, all of your strings have negligible mass. Because in order to deal with strings of varying mass, you actually need to do some integrals, right? So let's suppose we have this is an example. Um, we have a cable that weighs 2 pounds per feet, attached to a bucket filled with coal that weighs 800 pounds. The bucket is at the bottom of a 500-foot shaft. A, how much work does it take to lift the bucket from the bottom to the midpoint? And B, how much work does it take to lift the bucket from the midpoint to the top? So we have assumably some sort of a pulley, and a cable, and a big old bucket full of coal at the bottom. And we want to know how much force it takes to lift the bucket first from the bottom up to the midpoint. That's the first 250 feet. And then we want to know how much it takes to lift the second 250 feet. So the mass will not be constant here, because at the very beginning, we do need to lift the entirety of the cable. But by the time we're halfway through, half of the cable will be up above. We won't have to lift that half of the cable. So the amount of mass that we're trying to pull up is decreasing the further we pull it up. So we need to parameterize. So first off, the amount of force that's happening will be from gravity. It'll be 9.8 times the mass. Well, what is the mass we're lifting? Well, the mass we're lifting is the mass of the bucket plus the mass of the cable. The mass of the bucket is easy. That's 800 pounds. The mass of the cable is a little bit trickier, right? So the mass of the cable needs to start at, well, it's 2 feet per cable for 500 feet of cable. So that'll be 500 times 2, which is 1,000 pounds. And end at 0 pounds. Because once the bucket's at the very top, at that very last instant, right before we were done, we're only lifting the bucket. We pulled all of the cable up, right? So this should decrease linearly. So let's let x be the distance from the top. In other words, how much more cable do we have to reel in? How much further does the bucket have to go? That's x, right? So x is the distance from the top. Then when x equals 500, the mass of the cable is 1,000. And when x equals 0, the mass of the cable is 0. So here, the mass of the cable equals 2x. So now we can set up our integral. Our integral for part A will be the integral from A to B of f of x dx, which will be the integral from A to B of 800 plus 2x dx. And x is the distance that remains. It's how much further we have to go. So we're lifting it from 500 feet to 250 feet. This is this feels a little bit backwards because we're used to our upper bound being larger than our lower bound. There is a way to parameterize this that involves, that basically allows this to be sort of the right way around, if you will. If alternatively, we could let x be the distance traveled by the bucket, then the mass of the cable is 1,000 minus 2x instead. And we get the integral from 0 to 250. This is again for the first half of the journey of 800 plus 1000 minus 2x dx. And these two integrals should result in the same result. So here we end up with 800x plus x squared evaluated between 500 and 250. So we just need to plug in. That'll be 800 times 250 plus 250 squared minus 800 times 500 plus 500 squared. Well, it was already multiplied by 2, right? It was 2x. Yep. That's okay. So that'll be 800 times 250 minus 250 squared minus, or that shouldn't be minus, that should be plus. Which gives us, well, negative 387,500. Foot-pounds. That should have been a positive number. Let me think about my parameterization for a second. It is the distance from the top. So we do want to be going from 500 to 250. No, it would mean that the work is done in the opposite. So work is a vector quantity because distance is a vector quantity. So the work is done. Basically, what this means is that the work is done in the opposite direction. And I want to say, so if we change it from 500 to 2, from the integral from 250 to 500 of f of x dx, switching the bounds like that will just result in switching the signs. The number is correct either way. It should be definitely 387,500 feet-pounds. Let's check the other integral and verify and see what result this one gives us. I think this one should give us the same result. So this one here will be the integral from 0 to 250 of 1800 minus 2x dx. So that'll be 1800x minus x squared evaluated between 0 and 250. So that one will be yeah, so I think maybe I just didn't need to switch the bounds. I think maybe the bounds should have been in the conventional direction. So this is also just 387,500. So it's probably reasonable to use some common sense and note that this number should in fact be positive. And apparently don't be an idiot like me and switch the bounds. For part B, we have to do a similar integral. In the first parameterization, this time we'll have the integral from 0 to 250 of 800 minus 2x dx, which will be 800x minus x, sorry, plus 2x plus x squared, evaluated between 0 and 250, which will be $262,500 foot-pounds. With the other parameterization, that'll be the integral from 250 to 500 of 1800 minus 2x dx, or 1800 x minus x squared from 0 to, or from 250 to 500. Which of course gives us the exact same number. So, as a note here, the force, or the work done to lift the bucket halfway is very dependent. It is very different depending on which half you're talking about. Okay. The first half, so when you're pulling the bucket up, the first half, it requires significantly more work than pulling the bucket up the second half. All right. The last application that I want to walk through real quickly is actually from the textbook. And it's an application of, it's actually an application that mixes some optimization um, with some integration stuff, right? So the question is, at what angle should you launch an object to maximize its horizontal travel distance? So this is going to be us taking a step back from trying to be more sophisticated at physics, and we're going to imagine that we live in a magical world with no air resistance. Because air resistance actually makes this a slightly different problem. So, on one hand, if you point the cannon too low, you won't get as much distance as you possibly could because there won't be enough hang time. And if you point the cannon too high, the horizontal velocity will be too small and it won't actually maximize the travel distance, right? So, basically, if we point it too low, we're not going to go very far. And if we point it too high, we're not going to go very far either. So, because this is a mathematical thing, we're just going to try and work with the nicest possible numbers. So we're going to say that the force expended by the cannon is 1 unit, Newton, if you prefer. So essentially, we're shooting at a projectile, and we want to know what the horizontal component and what the vertical component of the force is. We're going back to that same idea when we talked about pushing the box. When we deal with a force at an angle, we typically want to separate it into two component forces. We want to deal with a vertical force and a horizontal force, right? So based on this angle theta, this is F, then of course F sub x will be cosine of theta, and F sub y will be sine of theta. So we basically have two parallel universes happening at the same time here. We have the x-axis forces and the y-axis forces. On the x-axis, we should end up with a position function, s of t. We'll even call it x of t, actually. We should have a velocity function, v sub x of t, and we should have an acceleration function, a sub x of t. In the y-axis, we should have a position function, which will be y of t. We should have a velocity function, which will be v sub y of t. And we should have an acceleration function, which will be a sub y of t. So because we're assuming an instantaneous impulse of the on the projectile, we should know that our velocity function for v sub x, our velocity should be constant. It'll just be cosine of theta. There's no force working backwards on us, and there's no force acting forward on us, right? In terms of the x coordinates. So the acceleration will be 0. And the position function we're going to hold on to for a second. In the y coordinates, we know that the y acceleration, there is actually a y acceleration. There's the force of gravity is pulling the projectile downwards. A sub y of t is equal to negative 32, or, well, sorry, we're in meters, so negative 9.8 meters per second squared. We do know, however, that v sub y of t is going to be, well, we know that when t is equal to 0, v sub y of t is going to be sine of theta. Our y velocity of our projectile should be sine of theta, because that's the velocity imparted by the instantaneous impulse from the cannon. So that means that our velocity function is actually v sub y is equal to, well, this is actually it's actually a differential equation. We know that dv over dt, the derivative of velocity with respect to time, is equal to negative 9.8, and we know that v sub y of 0 is equal to sine of theta. So this is a separable differential equation. So d v sub y is equal to negative 9.8 dt. And we can integrate both sides here to get that the integral of 1 times the integral of 1 dv sub y is just going to be v sub y. And on the right-hand side, we'll get negative 9.8 t plus a constant. What is that constant? Well, let's use our initial condition. V sub y of 0 is equal to sine of theta. So that means that sine of theta is equal to negative 9.8 times 0 plus a constant. So our constant is just sine of theta. So v of y of t is negative 9.8 t plus sine theta. We can also use a differential equation now to solve for y of t. So we know that dy, or yeah, dy over dt, which is our y velocity function, is equal to negative 9.8 t plus sine of theta. So the integral dy is equal to the integral of negative 9.8 t plus sine theta dt. So that means that y is equal to negative 4.9 t squared plus t sine theta plus another constant. This constant here, we can also solve for using an initial condition. Here, question? Sorry. Here, our initial condition is y of 0 is equal to 0. At the instant we fire our projectile, the height will be 0 because it won't have gone anywhere yet. So we get that 0 is equal to negative 4.9 t squared plus 4.9 times 0 squared plus 0 sine theta plus c. And this tells us that 0 is equal to this c. So our velocity or our position function here is negative 4.9 t squared plus t sine theta. There's just a little bit of work left over here on the left-hand side. We can find our position function, x of t, by, again, solving a differential equation. Dx over dt is equal to cosine of theta. So the integral dx is equal to the integral of cosine of theta dt. So that means that x is equal to t cosine of theta plus a constant. And once again, our initial condition is that x of 0 is equal to 0. So that means that 0 is equal to 0 cosine theta plus c. So here the constant will be 0. So our position function here will just be t cosine theta plus 0. So we've done more work than we actually need to. On the left-hand side, this stuff on the x-axis side here, this is really all we needed to find our optimal angle, which is not going to be a very surprising result. But notice on the right-hand side here, through applying a separable differential equation, we've actually derived basically one of the kinematic equations for that is used consistently in algebra-based physics. So in just sort of as a side note, we'll come back to the initial question in a second. I want to talk a little bit about kinematic formulas. So the kinematic equations, and two particularly important ones, one of them is that v final is equal to the initial velocity plus acceleration times time, where a is constant. Note, this is exactly what we got from solving the differential equation, dv over dt is equal to a with initial condition v of 0 is equal to the initial. So again, we could say that dv is equal to a dt. We can integrate both sides. We get that v is equal to at plus a constant. And then plugging in here, we get that the initial velocity is equal to at plus, a times 0 plus a constant. So the constant is equal to the initial velocity. And we get exactly that formula. V is equal to at plus the initial velocity. And another kinematic equation that shows up a bunch is that delta x, the change in x, or the distance traveled, is equal to the initial velocity times time plus, or actually I should say the x position is equal to the initial x plus the initial velocity times time plus 1/2 of at squared. And this is exactly received by solving this separable differential equation, that v is equal to at plus c, or more specifically, that the final velocity is equal to v sub I plus at, right? So v is equal to dx over dt. Velocity is the change in x divided by the change in time. And that's equal to, so dx over dt is equal to the initial velocity plus acceleration times time. Again, a separable differential equation. Dx is equal to v sub I plus at dt. We can integrate both sides to get that x is equal to v sub I t plus at squared over 2 plus a constant. And then our constant is just found with the initial condition that x of 0 is equal to x sub I. So x sub I is equal to v sub I times 0 plus a times 0 squared over 2 plus x sub I, plus c. Again, our non-constant terms disappear. We get that the constant here is x sub I, and we get our second kinematic equation that x of t, the x position with respect to time, is equal to the initial position of x plus the initial velocity of x times t plus the acceleration of x times t squared over 2. So a lot of these kinematic equations are just an application of calculus. The nice thing about this calculus-based approach, it feels like, oh, well, why don't we just use the stupid formulas? It seems like a lot of work just to get these relatively simple formulas. The key to this approach, using the differential equations here, is that this works when acceleration is not constant. If your acceleration is changing, right, with respect to whatever, this approach still works, right? And as you become more adept with calculus and as you see more situations, you can deal with a ton of other different situations by applying these same ideas. Okay? Does anybody have any questions about these two kinematic equations here? And the process of going from acceleration to position using either differential equations or integrals? I'm sure that there has to be at least one question, but it's okay if you don't know what the question is yet. All right. Let's go back to our projectile. So recall in our projectile case, we decided that x of t is equal to t cosine of theta, and y of t is equal to negative negative 4.9 t squared plus t sine of theta. So notably, this equation over here on the right will tell us, so we can use this to solve for when the projectile returns to the ground in terms of theta. So based on the angle, when is the projectile going to come back to the ground? Then we can substitute that in here. Then optimize for theta between 0 and pi over 2. So y of t is equal to negative 4.9 t squared plus t sine theta. So that means that y of t is equal to negative 4.9 t plus sine theta times t. And this has two roots, right? So either negative 4.9 t plus sine theta equals 0, or t is equal to 0. This smaller root at t is equal to 0, that's just our initial spot, right? That tells us that we started at 0. This other root over here from the negative 4.9 t plus sine theta, this one actually matters a little bit. We can solve for t. Negative 4.9 t is equal to negative sine theta. So t is equal to sine theta over 4.9. So this is the time when projectile returns to Earth. We can substitute this time back into our other equation. X of t, well, x is equal to t cosine of theta. So that means that x is equal to sine theta cosine theta. over 4.9. And now we can find an absolute maximum for x in terms of the angle. And I think that's where I'm going to end, actually, because what I want you guys to do is, so part of your practice for today, well, optimization is something we covered this year, and our final is cumulative. So it's not a terrible idea to try, and we finish setting up this optimization problem. Let's go through the steps and have you find this absolute maximum on this interval. Okay? So I will also post a couple of um, application problems, and I will post a review guide after that. Um, but start with this. Start with this optimization. It should not be a surprise that to anybody that the correct angle here should be pi over 2. Or sorry, pi over 4. Um, it's a 45-degree angle is the optimal angle to shoot something at in a world with no air resistance. So you should know what answer you should get. Just make sure that you can actually get there. You remember that you're finding critical points, you're stating your endpoints, and you're testing your critical points and your endpoints to decide which one gives you the absolute largest value possible. Okay. Does anybody have any questions about what we covered today before I let you guys get to practice? Okay. In that